Hi, this video is part of the Chapter 2 highlights on the topic of frequency distributions. First of all, we want to look at our reasons for constructing frequency distributions. One of the main reasons is that if we have a data set, especially a large data set, we can summarize it with a distribution. Another good reason for doing this is that we can gain some insight into the nature of the data by looking at the frequency distribution. And third, it gives us a basis for constructing important graphs, such as histograms. When we talk about frequency distribution, there are several terms that you're going to need to know. So the first one of these is the lower class limits. When we look at a frequency distribution such as this one, for the ages of best actresses, the lower class limits are going to be the bottom numbers that define each class. So all of those numbers circled in red are the lower class limits for each different class. The upper class limits, you can probably guess, are going to be the top numbers on each class. And notice here that the upper class limits and the lower class limits are never the same number. That way, each one of our data values can only fit into one class. The class midpoints, we have to know to do some specific things later on. So to get these, we're just going to average the upper and the lower class limit from each class. So for example, in this first class, we would average 21 and 30. In other words, add them together and divide by 2 to get 25.5, and that's our class midpoint. The class width, this is one of the hardest items in frequency distributions to get. It's easy to look at a frequency distribution like this and think that the class width would be 9, because that's the difference between the upper and the lower class limits in any one of these classes. But that's not the case. To get the class width, you have to look at 2 consecutive classes and look at the difference between either their lower class limits or their upper class limits. So in any one of these, say in these first 2 classes, if we look at the difference between 31 and 21, the 2 lower class limits, the difference would be 10. So that is our class width. Okay, how to go about constructing a frequency distribution. The basic idea is that we want to look at our data values and we want to divide the whole range of data values into equal groups or classes. And then we want to count how many data values are in each class. This is what gives us the frequencies. So we're going to look at another set of data. This happens to be ages of best actors who won the Academy Award. So step 1 is going to be to find our class width. Now we can do this a couple of different ways. We can decide on how many classes we want, and the number of classes really should be between 5 and 20. Or we can decide on the class width if that makes more sense for our data. If you decide on the number of classes first, then to find the class width, you use this formula. You take the range divided by the number of classes, and then you round up to the next whole number. And remember, by range, we mean the maximum data value minus the minimum data value. So in this case, our maximum data value is 76. Our minimum value is 29, so our range would be 47. If, say, we decided to use 9 classes, then the class width would be 47 divided by 9, which would round up to 6. If we're talking about ages, 6 may not be an especially helpful value. So in this case, it would probably make more sense to decide on a class width instead. 10 years would be a convenient width to use, and it would be easier to understand. We're used to thinking of ages in decades. Okay, so if we decide on our class width of 10, then the next thing we need to do is find a starting point for our frequency distribution. This will be our lower class limit for the first class. And then once we have that, we can get the rest of the lower class limits. Again, for the starting point we have a choice. It can just be the minimum data value, or it can be a number less than that if it makes more sense with the data. And in this case, since we decided to go with decades for our classes, we would probably want to start with the beginning of a decade, like 10 or 20. Okay, in this case our minimum value was 29, but that doesn't make a lot of sense to start with if we're going to use a class width of 10, so we could use either 20 or 25 as a good starting point. For this example, we're going to use 20. Okay, so we start with our first lower class limit of 20. If our class width is 10, then we're going to write down the rest of our lower class limits just by adding 10. So here's the beginning of our frequency table. Then the next step is to find the upper class limits. And the easy way to do this is to look at the lower class limit of the next class and just subtract 1. Remember that upper and lower class limits can never be the same number. Now in this case our data is measured in units, so we're talking about subtracting 1. Sometimes we have data values measured in different units, such as tenths, so in that case we would subtract 1/10 to get our upper class limit. Okay, so again, if we're looking at our lower class limit for the second class is 30, that means our upper class limit here is 1 less than that, so that would be 29. And notice when you get all these upper class limits done, they all differ by 10 also. Okay, so now we've got enough classes here that we can fit each one of the data values into one of these classes. There's no data value that will be left out, and each data value will only be able to fit into one of these classes. Now the final step is to find the frequency for each class. In other words, look at all the data, go through and mark which class it fits into. You can do tally marks or whatever, and then count them up, and that gives you your frequency. So it turns out in this case, our highest frequency class was from 40 to 49 years old. Now for relative and percent frequency distributions, these have the same class limits as a frequency distribution, but the frequency is replaced with a relative frequency, which is a fraction, or a percentage frequency. So to get the relative frequency, you need the sum of all the frequencies that were in your original frequency table. So in other words, take all the frequencies and add them up. Get the total, and then for each class, to get its relative frequency, you divide that class's frequency by the total. To get a percentage frequency, you just take those relative frequencies and multiply by 100. All you're doing is converting from decimal form to percentage form. Relative frequency distributions are very helpful if you are comparing two sets of data, especially when you've got different numbers of data values in the two sets. So here's an example of getting the relative or the percent frequency distribution. The first step is to find the total of the frequencies. This was our frequency distribution we had before, so we just want to total up those frequencies. That total is going to be 76. Next, we're going to take each frequency of each class and divide it by 76 to get our relative frequencies. So for this first class, 1 divided by 76 is 0.01. And notice on all of these I rounded to 2 decimal places. You will usually have some kind of clue as to how many decimal places you're supposed to round to. In this one, I chose to round them all to 2 decimals. So for each one of these, we divided by 76, rounded to 2 decimal places, and that gives us our relative frequency. And notice that if you add up your relative frequencies, the total of that should be 1. There may be some rounding errors, so it may end up being 0.99 or 1.01. That's not necessarily a problem. If it's off by any more than that, then you should probably go back and check your work. You may have made a mistake. Then for the percent frequency, we're just going to take each one of those relative frequencies and multiply it by 100 to convert to percents. And again, with the percent frequency, your total, if you add all those up, should be 100%. Again, you can get some rounding errors, so it may come out to be 99 or 101%, but you shouldn't be off by more than that. Okay, here's an example of comparing 2 data sets by using relative or percent frequency distributions. Notice we have these 2 frequency distributions. One is ages of drivers killed in car accidents. The other is ages of drivers killed in motorcycle accidents. And obviously there weren't as many drivers killed in motorcycle accidents in this particular study. So it's hard to tell from looking at these 2 data sets how they really compare. The numbers, the totals are so much different. If we take each one of these frequency distributions and create a relative or a percent frequency distribution, then we'll have a better basis for comparison. So here's the percent frequency distribution for the drivers killed in car accidents, and here's the one for drivers killed in motorcycle accidents. By doing this, we can see that in this case, the 20 to 29 age group for the motorcycle accidents had a much higher frequency than for the car accidents. And also notice in this case that for the motorcycles, there are no values for ages above 59. In any case, this gives us a much better way to compare the 2 sets.